I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for the students, this class. Just ask you to be glorified in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. I think the microphone makes a clicky sound. If I put it over here, I think it doesn't. I'm going to try this again. I probably need to buy a new mic, honestly. Let's see here. Okay, so begin by talking about fractional residues. This is my section 10.5. So kind of neat. So this allows us to deal with the case that there's a singular point, like on the edge of a region we're interested in. And so here's the theorem. If Z naught is a simple pole of F and C sub epsilon is an arc of Z minus Z naught modulus equal to epsilon of angle alpha, then the limit as epsilon goes to 0 of the integral along C epsilon of f of z dz is equal to alpha I times the residue of f of z at z naught. All right, and this one isn't too hard to prove, so let's look at it. So proof goes like this. Since Z naught is simple pole, we can write for Z close to Z naught, we have that f of z is equal to, let's see here, a sub minus 1 over z minus z naught plus g of z, where g of z is holomorphic, or if you like, analytic at z naught, right? Now, C epsilon we can describe as z equals to z naught plus epsilon e to the I theta, where theta naught is less than or equal to alpha is less than or equal to, oh, did I say alpha? That's wrong. Theta. Theta is the variable here. Alpha is fixed. Theta naught less than theta naught plus alpha. So that's a arc of angle alpha. Let's see here. Notice that since G is holomorphic, right, the modulus of G of Z is less than or equal to M for Z in C epsilon, right? That follows because for some M, right? Why? Because G of Z is holomorphic, right? So it's certainly continuous, and as such it can be bounded because we're looking at a just an arc here. All right, so that said, we can now calculate the integral, right? So the integral over C epsilon of f of z dz is equal to the integral over C epsilon of a sub minus 1 over z minus z naught dz plus the integral over C epsilon of g of z dz, right? But notice that the integral, the g part, we can think about that. So like the absolute value of the integral over c epsilon of g of z dz, right? By the ML theorem is less than or equal to m times the length of c epsilon. But what's the length of c epsilon? So like here's, you know, all right. Here's a picture of it. So the length of it is just what?
R.
R alpha, which, and R is what here? It's epsilon, right? So the radius is epsilon, so epsilon alpha. M epsilon alpha is that, right? On the other hand, the other piece of this, the integral, this one, let's just calculate it, right? So this would be the integral of a sub minus 1, and remember z is equal to this right here, right? So dz is what? I epsilon e to the I theta d theta. We're integrating from theta naught to theta naught plus epsilon. And we got to divide by z minus z naught, which is epsilon e to the I theta, right? How's that work out? Every once in a while. So those cancel. These cancel. And you're just left with a sub minus 1 times I times alpha. Right. So therefore, we have the limit, we're looking at the limit as epsilon goes to 0 of the integral of c epsilon f of z dz, right, is equal to the limit as epsilon goes to 0 of a sub minus 1 I alpha. I mean, it's less than or equal to this, right? Well, let me not say that. It's equal to this, right? Because what happens to this piece here as epsilon goes to 0? This does what? See, because of this right here. Right. I mean, I'll give you another step here in just a second. So this is a sub, these are just constant, a sub minus 1 I a sub minus 1 alpha. Notice that the limit as epsilon goes to 0 of the absolute value of the integral over c epsilon of g of z dz, right, is less than or equal to the limit as epsilon goes to 0 of m epsilon alpha, but that is equal to 0, right? Which then proves that the integral over the holomorphic part of it just goes to 0. So there you go. This is the fractional residue theorem. See how this works? If we encircle the whole residue, what does this become? Alpha becomes what? 2 pi, right? So it goes back to the regular residue theorem if you look at that limit. All right. See if I can find a good example here. All right, so not like that example that much. Wheel. I guess we'll try this one. Example 1. So let's see here. All right. So we've got two square root of 3 times I up here. I've got minus 2 square root of 3 times I down here. And look at the circular path. That was supposed to be circular. Use your imagination like that. All right, so minus 2 is like in here somewhere. So, all right. Here's the problem as I've stated. I say like gamma of t equal to 2 square root of 3 e to the it, or pi over 2, less than or equal to t, less than or equal to 3 pi over 2. All right? And then I say calculate the integral over gamma of dz over z plus 2. All right? So how would you, well, let's do this a couple different ways. Let's not, so the one way to do it is just to use, like, what's the problem with this? I can't just use, okay, you guys tell me, why can't I do this? You know, endpoints. Well, where does it start? It starts here, doesn't it? No, I'm an idiot. Starting point starts, right? Eventually, I'll remember how to do calculus. All right, so why can't I do that? You're fine.
Oh, it's discontinuous, right?
Right, because the log has the branch cut, like over here, right? If we have z equals to minus 3, for example, that's where there's the discontinuity of log z plus 2. So to fix this, it's simple. We don't use the wrong log. We use this one, right? So that log 0, no, that has the branch cut like over here, right? Okay? So we can do that, and so let's do it. We've got log sub 0 of, let's see here, 2 plus 2 root 3I minus log sub 0 of, let's see here, minus, 2 rather, minus 2 root 3I. So both of these numbers have the same magnitude, right? So like the real part's going to cancel out, right? You got like natural log of the modulus of square root of 4 plus 12, I guess. And then plus I arg naught of 2 plus 2 root 3I minus the natural log of the square root of 16 again, you know, minus I arg naught of 2 minus 2 root 3I. So these pieces cancel, right? And it's just the imaginary part. And notice we can also say, well, that's really just I times arg naught of 1 plus I root 3, you know, minus I times arg of 1 minus I root 3. Because if you take a scalar multiple, the angle is the same, right? So we can drop the 2's. And so notice that the tangent of pi over 3 is equal to the square root of 3, because tangent of pi over 3 would be sine of pi over 3 divided by cosine of pi over 3, which is root 3 over 2 divided by 1/2, which is root 3. But if you, of course, look at a triangle, root 3, 1, right? That's this point right here, 1 plus I root 3. So this angle is pi over 3. So we get I times pi over 3 minus I times minus pi over 3. So it works out to what? Looks like 2 pi I divided by 3. Uh-oh. Yowzers. Well, I did something wrong. No. Dummy. So, what did I do wrong? This one I think is okay, but where does arg naught follow in? Like, arg sub 0 of whatever is between what? Right? By definition, arg sub 0 takes an angle between 0 and 2 pi. Minus pi over 3 would be the principal argument of that, but that's the wrong one, right? So this is not right. What should I have here instead? Which is? Yeah, 5 pi over 3.
That took too long.
That's okay. So we've got minus 4 pi over 3, I think, if I didn't make another mistake here. Hopefully. Which I somehow have got the, Oh, wait a minute. Okay, come on, flag on the play here. Come on, guys, like this is, what's the orientation here? This is counterclockwise, right? Which is like this. So this is the starting point. This is the ending point. So, yeah, we need a minus. Unless you want me to, I'm just going to put, yeah. If you don't mind, I'm just going to do it like this. There we go. Okay, so that's how do I calculate that integral directly. But maybe there's another way we could do this with the fractional residue theorem. Yeah? So think about it this way. We're going So we start here. What's that? What parentheses? What are you talking about?
In your picture in the middle.
Is equals to.
Oh. Hey. Let's see here. All right, so here's my minus 2, you know? If I make this kind of region here, right? And then when I get here, I make a little like that, right? A little C epsilon there, right? See that? So let's see here. We want to go counterclockwise, so we're going to go like this, then like this, and then like that, right? Yeah. So then, if I was to do that, if I call this region D, like the integral of dz over z plus 2 over, you know, the boundary of D should be equal to what? Zero, I think, because it's holomorphic in there, right? Yeah. But on the other hand, we also have that the integral along gamma of dz over z plus 2 plus the integral along, let me call this one like, I'll call this L plus and I'll call this L minus. L plus dz over z plus 2 plus the integral of dz over z plus 2 L minus plus the integral over C epsilon of dz over z plus 2. This should all be equal to 0. So if we can calculate, and so in the limit as epsilon goes to 0, this goes to what? Not 0. Mm-mm. So if you look at this, so this is pi over 3 here, and this is pi over 3 down there, right? So what do you have? What's the arc length? Length of the arc, and what's the angle subtended on the other side? What's this angle here? Alpha equals to what? Yeah, 4 pi over 3. To check, we should have this plus that gives me 2 pi. 6 pi over 3, 2 pi. Cool. So if we use the fractional residue theorem, this should give us 4 pi over 3 times the residue of 1 over z plus 2 at minus 2 times I, right? That was the there's an I in the residue theorem. Alpha I residue. Don't forget the I. But what is the residue? It's just 1, right? This is literally just the term, the reciprocal term in the Laurent series. So it's a very silly Laurent series. But yeah, 4 pi over 3 is that. Rats. Or did I do it wrong? Hold on a second. I bet it's a minus. Let's be more careful. If this is going like this, it's coming back in here. What's the orientation of that loop? It's clockwise. Clockwise. Which means that there's a minus here and here. That's the modified fractional residue theorem, right? So what this means is that there's some argument that can be given to see that the integral, the L plus and the L minus integrals cancel out, apparently. Or they're both 0. I don't think they're 0. Anyway, that's my example. It's not a great example, but there's an example of how you can use okay. So in the notes, I straight up calculate the integral along the rays, and I'll show you what I got. So the integral along -2 -2 to plus or minus 2I root 3 of dz over z plus 2. It works out to minus the natural log of epsilon. But you notice that the L minus takes the starting point. Okay, so like L plus is equal to minus 2 to 2I root 3, right? But L minus is actually minus 2I root 3 to minus 2. So those being equal means that they cancel. However, notice that both of them are blowing up in the limit as epsilon goes to 0. So you actually you really would need to package this as a limit and take the epsilon going to 0 and cancel these out inside the limit. You can't take the limit separately and cancel them, because each of these integrals as epsilon goes to 0 is separately divergent. But they do happen to cancel in this. So, as I said in the notes, I think this example is kind of dangerous. I have a more standard but boring example right before it for you to look at if you want to. All right, let us move on. So next up, we have, you'll like this one, Jordan, Jordan's lemma. So lemma, if CR is semicircular contour given by like z theta, z as a function of theta is r e to the I theta, 0 less than or equal to theta less than or equal to pi in the upper half plane. Then the integral along CR of the value modulus really of e to the I z modulus of dz is less than pi. So that's the arc length integral. All right. Integral with respect to arc length we defined a while ago. So this is Jordan's lemma. I will not prove it. Proof is in the notes. Proof isn't particularly interesting. Its application, though, is pretty cool. And here we actually will get a chance to see the fractional residue again. And here's how it goes. We're going to look at the integral from 0 to infinity of sine x over x dx. We're going to show that this is equal to pi over 2. Let's see why. To do this, we calculate the integral of f of z equals e to the I z over z. We're going to do it over a so-called indented contour. So here's how that goes. It's like a half circle. It goes from minus r, and here's 0 in the middle. All right, we do a little one of these C epsilon deals, and r is over here. So it goes like this, goes like that. I'll call CR the upper half circle, just like in Jordan's lemma there. C epsilon, right? So do we, hopefully we all can understand the contour we're interested in here. So I'm going to call this, well, that's the contour of interest. And what we're going to do is we're going to look at the integral, the absolute value of the integral over CR of e to the iz over z dz. Let's see why that's interesting. So this, of course, is less than or equal to the integral over CR of the modulus of e to the iz over z.
Did you mean to write sin x over x?
dz. Yes, I did. But in this context, if we're on the semicircle of radius r, this is just r, right? So we have equal to, integral 1 over r CR absolute value of e to the iz dz, right? And then here comes Jordan's lemma. Jordan's lemma is really just like trigonometry. It's just like a pre-calculus, Calc 2 kind of argument. It's nothing. I don't think it meaningfully uses the techniques in this course or anything. It's just a technical result, really. And so this is less than what? Pi. So we've got pi over r. Right. So what happens to this? This goes to 0, right? As r goes to infinity. So if we integrate around this contour, let's see here. So if we think of f of z, let me think of gamma as the, all of the above. All right, so like, let me just say it, the whole curve, okay? So what should the integral over gamma of, e to the iz over z dz be equal to? 0, right? That's for epsilon. And so technically, gamma is really a function of epsilon and r, isn't it? And I can only say this technically for epsilon greater than 0 and for r greater than whatever, I don't know. Let's say greater than, I mean, it doesn't matter, but let's just say 0. Obviously, that doesn't quite make sense. Of course, you need that the epsilon is smaller than the r, right? I mean, I'm not going to fuss about it because we're going to look at two limits simultaneously. The one is epsilon pinching to 0, and the other one is r going to infinity. We're going to impose both of those at the same time for this contour. Now, obviously, as r goes to infinity, the integral over CR goes to 0, right? So, and this is equal to 0 because there is no singularity of e to the iz over z inside this region, right? You guys get that? Okay, so what we then have is, goodness gracious, I need to try to follow my notation here. All right, I'm going to ignore the notes for a second here then. So what are these points specifically? What's this? This is, nope. It's just epsilon. See, because, yeah, and then this one here is, yeah, minus epsilon. So let's put it all together. We've got the integral. I guess I'll just write it all out. So we have the integral over CR of e to the iz over z dz, right? Plus the integral from minus r to minus epsilon. And I'm just going to take and union that with the other one, so I don't have to write so much. Also epsilon. My epsilon just became a 3. That's not a good sign. Epsilon to r. So those are the, you know, the along the x-axis ones, right? E to the iz dz over z dz plus the integral over c epsilon of e to the iz over z dz. I think that's it, right? I mean, I've got these two segments, which I wrote as one. Yeah, that's it. Now, the c epsilon, what's the orientation? That looks, warning, this is clockwise, right? C epsilon's clockwise. So when we use the fractional residue theorem to calculate that, we need a minus, right? So as r goes to infinity, this goes to 0, right? And as epsilon goes to 0, what happens here? Oh, by the way, this is all equal to 0, right? So limit as epsilon goes to 0 of the integral over the c epsilon e to the iz over z dz. What's the alpha in this case?
Pi.
Alpha's pi, right? So you get half a residue, right? But we get a minus here because it's clockwise. So we have minus pi I residue of e to the iz over z at 0. And how should we calculate this residue?
Rule 1.
It's equal to 1?
Oh, I said rule 1.
Oh, rule 1.
Also that.
You're right on both accounts. So this is equal to 1 by rule 1. Very good. Okay. So minus pi I then. Cool. So what we have in total here, and by the way, this, so how about this middle piece? Right? How about this? Here, z is equal to what? Z is equal to x. And dz is dx for this integral, right? So what this leaves us with is the integral of e to the ix dx over x, you know, and if you allow me this slight abuse, it really just goes from minus r to r because the epsilon's going to 0, so what we're left with is the limit as r goes to infinity of that, right, is equal to, so this piece drops out, and it's just equal to minus that. So if I bring the minus pi I over to the other side, I get pi I, right? So here we're letting epsilon go to 0 from the right to obtain that. But then what is e to the ix? We've got what? We got cosine of x plus I times the sine of x divided by x dx. And notice that that is cosine x over x is an odd function, so that integrates to 0. So this just leaves us with the limit as r goes to infinity of the integral from minus r to r of sine x over x dx. And I'm going to take the liberty of pulling an I out of all that. And that's equal to pi I. So therefore, the principal value of the integral from minus infinity to infinity of sine x dx over x is equal to pi. All right. And that implies that half the integral from 0 to infinity is pi over 2. Right, so from this, we can extrapolate that by the symmetry of the problem. This is also true. So this is, I think, a more interesting use of the fractional residue theorem than my previous example. My previous example is just kind of forced. This is a more natural and typical use of it. And also, we get to see Jordan's lemma. Woohoo! By the way, we should probably try to go back and solve that other problem that we got hung up on with Jordan's lemma. The one I told you guys, what's in my notes is just nonsense because I was using, it rested on the assumption that e to the iz, the modulus of e to the iz is 1, which just is not the case. Right? So we should at some point go back and try to fix that example. But not today. All right, so there are more examples in the notes, of course, and but I must move along here. So we will now turn the page and move on to the problem of the log integral. I guess technically I should spend a minute with you guys talking about the how to use residue theory to calculate a series. So there's kind of a trick there. But I think if you work through the problem in Nagel, Saff, and Snyder, then you should Nagel, listen to me, just Saff and Snyder. It should work out. Now, if that's not enough, there's also a handout on my website that a previous student of my brother's wrote, Noah Hughes, a few years ago. And that one is super helpful for understanding how you can use residue theory to calculate a series. Let me show you that for like 5 minutes, and then I'll get back to writing stuff out here. So on the course website, it's like it's not in Canvas, but if you look at the website I made for the course, it's in there. Come on. Wake up. Fine, I Control-Alt-Delete you. Take that, foul computer. All right. Here we go. Come on, come back. All right, so here's the course website, and if you look down here, I have this infinite series in the residue theorem by Noah A. Hughes. That is very helpful for those homework problems. I'll just run through it with you guys here. So if you want to calculate a series, you can use the residue theorem in a kind of circuitous way to do it. Now, I think part of the homework problem I assigned you guys from Saff and Snyder may be deriving certain aspects of what's in this handout. So my apologies if I am inadvertently showing you how to do part of your homework. Anyway. So this actually has a, rats. There we go. So he builds up the problem. So like this has a little bit of like what is the residue theorem and all that at the start of it. We don't care about that. We already know it. So the problem developed in this little PDF is how you can calculate infinite series of the form like minus infinity to infinity. All right. And so to do that, he looks at f of z times a g of z, where this g of z is some hypothetical function which only has simple poles, and they're just at the integers. It turns out like cotangent of pi z is such a function, so that's typically what's used. Cotangent of pi z, you can choose that to be g of z. That's actually got a simple pole at at like all the integers. So if you think about this function, g of z times f of z, it's only going to have singular points in this lovely rectangle here at the integers, and then wherever else f happens to be singular, which is going to be some like finite collection, all right? Then what's done is you note that, well, the integral along this rectangle, which is called Cn, is 2 pi I times the residues of the product of g and f of z within the Cn. And then arguments are given to show that this integral has to go to 0, because basically this function is going to be bounded on the rectangle, all right? And so it turns out that the integral around the rectangle is 0, which then allows you to equate some of the residues against the others. So there's two different kinds of residues: the residues that are integers, and there's the residues which are appearing because f of z has a singularity, and you're able to equate those two with a minus by the residue theorem. That's the long and short of it. So like, I'll get to the point here. These are the details of why what I just said happens. It leads us to the summation theorem. And the summation theorem says this: if you have a function that's analytic except for a finite set of isolated singularities, and it's bounded like this, so m over z to the power k for some k greater than 1, then the integral from minus infinity to infinity of f of n is equal to minus the residues of pi cotangent pi z f of z at f poles. That's, there's obviously some details that I've skipped over here, but that's how you can calculate that. And that's really cool, because that gives us yet another way to like calculate infinite series in a kind of circuitous fashion. See if I can find an example here, like this one. So you can prove that 1 over n squared plus a squared is equal to pi over 2a hyperbolic cotangent of pi minus that. All right, so like what you do, how can you get your pause on this from the integral from minus infinity to infinity of that? Well, this, if this is equal to that, I've got like minus infinity to minus 1, here's the term at 0, and here's the term from 1 to infinity. So this and that are actually the same because it's an even function, so you can double up those plus 1 over I squared, so that gives you this. Let's see here. So here's another one. Why is this equal to pi squared? Well, if we let f of z be, that's of z, 1 over z minus 1/2 squared, it has a double pole at 1/2. And so the residue of pi cotangent pi z over that at 1/2 is equal to this. It's basically rule 2, right? Which ends up giving you minus pi squared. So we have that this is equal to pi squared. And then if you wanted to, you could use this to figure out what the sum from n equals like 1 to infinity of n minus 1/2 was equal to, right? You could just, it's double, this is like twice it, and then the term, the previous example, like split it minus infinity to minus 1, then the 0 term, and then 1 to infinity. So you could get your pause on the integral from 1 to infinity from this if you wanted to. But that's pretty much it. So like, here's a rather famous example. So like the p equals 2 series, which is, it converges to pi squared over 6, as it turns out. And here's one way you can look at that. If we look at f of z is 1 over z squared cotangent z, it has a simple pole at 0. This is the Laurent series. Multiply, collect terms. Then this is that. So you can read off the residue is pi squared over 3 with a minus, right? And so the only singularity of this happens to be at 0. And so that gives us that this is equal to pi squared over 3, which then, what about 0? Aye. Oi. What about 0? That's troubling me. Well, there's something I don't understand there. Let's stop looking at this one. But let me put it this way. So there was nothing to see there. What's that?
Did you see a student write that?
Yeah. Yeah, that was one of my brother's better students over the years. So he might have been a grad student at that point. I don't know. Maybe. All right, so next up here. So you have a token homework problem or two on what I just was showing you briefly. So try to do it. If you figure it out, great. If you don't, it's not the end of the world. Certainly the integrals that we've been doing are much more likely to be tested. To whom much is given, much is required. I haven't given you much about the series calculation, right? So next up, we must talk about what is known as the logarithmic integral. All right, and so this will take a bit, and it's just one piece after the other, but we'll start with what's called the argument principle. And so I don't believe this is in any direct way a yet another application of residue theory. So we're really doing something different for a change at the moment. So here's the definition. So we're in my chapter 11 now. Suppose f is analytic. On a domain D, right? For a curve gamma in D such that f of z is not equal to 0 on gamma, we say 1 over 2 pi I, the integral of f prime of z dz over f of z is the logarithmic integral of f of z along gamma. So this is actually, we could also write it as 1 over 2 pi I integral of the differential of the log of f of z along gamma. So this is the logarithmic integral of f of z along gamma. So just to get an understanding of like what this thing does, let's look at an example. So example 1, we'll look at f of z is just z minus z naught to the nth power. All right. So example 1, I guess we're on example 3, huh? Yeah. So f of z is z minus z naught to the power n. And we'll look at the curve gamma of z is z naught plus r e to the I theta for 0 less than or equal to theta less than or equal to 2 pi k. So that is, what we're doing there is we're taking the circle centered at z naught and we're going around it how many times? K-fold times, that's right. All right. So for this, if we calculate f prime of z over f of z, what do we get? Let's work it out here. What's f prime of z over f of z for this function? We get what? We get n z minus z naught to the n minus 1 divided by z minus z naught to the n.
You have to clarify that k is an integer, or does it not matter?
Yeah. I mean, I guess I better put positive integer given the rest of what I wrote, you know. Okay, so that is what? That's n over z minus z naught, right? So what happens when we actually calculate this integral? We have 1 over 2 pi I. The integral of what? F prime of z over f of z dz. So we've got 1 over 2 pi I integral from 0 to 2 pi k. And we're just going to have n r I e to the I theta d theta divided by, well, z minus z naught is what? It's r e to the I theta. So the i's cancel, the r's cancel, and we've got ourselves a n over 2 pi. The e to the I thetas cancel, right? What's left? Just the d theta, right? Like the only things left in here is d theta. See that? These cancel, the I cancels, the r cancels. I put the n here, kept the 2 pi. So we're just left with the integral of d theta. So we've got theta evaluated from 0 to 2 pi k. So that gives us, you know, n over 2 pi times 2 pi k, which is just n times k. So we say k is the so-called winding number of this curve. Which is what it sounds like. That's like if you imagine gamma as a string and you're wrapping it around, right? You wind it around k-fold times to cover this circle, yeah? So n, I guess I didn't say what n was, did I? But, so you should ask me, did you ask me about that? You asked me about the other one, but I should have said n is an element of the integers. See, n could be positive, it could be negative. All right? This calculation did not care. But what is n? It's what? It's either the order of the 0 if it's positive, right? Or it's the order